Thank you all for coming out this morning. Everyone looking awake? Yes? Can you get hands up, a little stretch? Hands out to the side. Come on, guys. Wake up your bodies. This will be a very interesting talk, I hope. So yes, I'm going to talk about mitigating parcel variability. So I'll skip the slide where I tell you what automated parcel handling is, since I imagine most of you know what that is, and go straight into parcel handling. In my mind, I think this is uncontroversial, is all about handling variation. Anyone disagree with that statement? Great. So automation, just a brief history, started with being accurate and precise. So you would have a system, an arm in this case, do the same thing over and over again. Repeat this exact motion. From there, we got a little more flexible. So we're going to handle objects that we know, but in different variations, different orientations. We're going to pick them out of piles. This was, really interesting work, really novel. We got a little more complicated. We started saying, all right, we're going to handle boxes now of various sizes and various shapes. And now we're moving into the world where we're handling all sorts of containers. So this is an example of an induction scenario. We've got flat packs, we've got envelopes, we've got boxes. Lots of variation that we need to deal with. I'm waiting for the day when someone asks me to handle these. Remember these from when you were kids? Little rubber water tubes that just slip out of your hands all the time. Someday we'll have to do that. Not today yet. So a question I ask when I go and look at a new customer, you want to automate your parcel handling. The question is, what's your distribution? What is the variety of things we need to be able to handle in your domain? And the answers I get tend to be one of these. We don't know. It's unknown. Either we don't track this or it's always changing. The changes could be seasonal, right? So as people shift their buying patterns, the things you need to ship change. We also change sometimes just for advertising or packaging science advances. And of course, new things are being developed all the time, and now you need to handle them. The big thing we've seen recently is SIOC, ship in original container, where now you no longer control what it is that you have to handle. It all looks different. So here's a little picture that I use to help me track of this. This is a distribution over packages. 2 dimensions, color and size. Of course, there are many, many, many more. This is just 2. This may be what we're focused on today. Brown cardboard boxes. They're fairly coherent, fairly consistent in color and size. But all of a sudden, it's Black Friday, and people start buying televisions. So the shape of your box has changed. It's still a cardboard box, but it looks different. Conversely, a new movie comes out, and someone decides it'd be a good idea to advertise that all over your boxes. All of a sudden, your color shifts. Everything looks different. I got a box the other day, literally arrived at my door, advertising Candy Crush. People know this game? This box is brightly colored. It has circles. It has squares on it. It is difficult. It is very different from a brown cardboard box. And of course, over time, these changes, TVs might get less popular, advertising might go away, you might go back to that original distribution. And so, summary is the distribution you need to handle changes over time. You also need to worry about these sort of 1 in a million situations, right? You've probably all heard of the 20-80 rule. 20% of your scenarios account for 80% of the actual things you need to manage. That could be very true, but there's still lots of other random things that will happen. One solution, that's not an alarm, one solution does not fit every possible scenario. And of course, if really anything is possible over a long enough time frame, anything could actually happen. Here's one of my favorite examples from a different domain. This is autonomous vehicles. This is a car driving down a road. There is a woman in a wheelchair chasing a duck across the street. I don't know if you can all see that in the top right corner. There's a little duck right in front of the car, and there's a woman chasing it. This is not a scenario that I would have considered had you told me to be in charge of testing an autonomous vehicle. It happened. The system needs to deal with this. So you need to build systems that can handle anything that might happen. And these situations are so rare and so unlikely that you have a long-tail distribution. And I said expect the unexpected, like we learned from DuckTales back in the day. So the long-tail distribution looks a bit like this. We have a few things that we see a lot of. We see a lot of brown boxes, we see a lot of envelopes, we see a lot of bags. That's the 20% of scenarios accounting for 80% of the things we handle. But there's also all these things that we see very rarely. We could see boxes that are hexagons instead of rectangles. We could see boxes that are brightly colored, like this Candy Crush box I saw. We could see a box shaped like a dog. It could happen. Someone could actually ship a potato. So you need to think when you're doing automated parcel handling, how am I going to handle these rare 1 in a million long-tailed situations? So this, to my mind, brings a dichotomy. Do you want a universal model, or do you want an adaptable model? A universal system or an adaptable system. And I'm going to define these as being able to handle anything, that's universal. Anything you give it, it can handle. Or being able to handle anything. That's an adaptable system. It's a system that can change over time to handle whatever you throw at it. A universal model, you have to spend a lot of time up front considering all the edge cases and how your system's going to handle that. You can do a lot of things, many of which you will never actually need to do. Right? I saw a duck crossing the road. Well, now I'm going to build a system to handle a zebra crossing a road. Will I ever need to do that? I don't know. The whole idea behind universal models is you build them once, and then you use it forever. And you measure the success of a universal model by how much of the space can you handle. Another little diagram. Again, this is that space, color, size, and the green is the area the system can handle. We can handle most of this space. This is a pretty good universal model. An adaptable model, on the other hand, focuses on what actually occurs. What do we actually see in the world? And the whole goal is to quickly absorb new things that we see into what I'm going to call the region of competency. This is that green area. Adaptable models inherently need to be built iteratively. They need to change over time, and you measure them by how well can they adapt. So here is an adaptable model. We have that region of brown cardboard boxes down here that we know, and then all of a sudden things change, and we measure how quickly can we shift what our system can handle to the new things we need to deal with. How does this tie into symbiotic human AI systems? Well, a symbiotic human AI system is a human and an autonomy working together. And I argue that this is what we do, right? No autonomous system is 100% successful. There's always some edge case, there's always an exception. And that's what the humans come in. So we currently build and distribute and deploy symbiotic human AI systems. The system itself is designed to be universal. Between the autonomy and the human, we can handle whatever happens. So the question really is, how universal does the autonomy need to be? How much can you rely on the human? And this comes down to how much human interventions do you need, how many do you need, and how much does it cost in terms of time and money? So let's talk about human interventions. There's a seesaw, there's a trade-off, like in most things. If human interventions are expensive, if they cost a lot, either in money or actual time, you need to have very few of them, because you just can't afford to have more. This means you really want to go for a universal autonomy. You want to minimize the number of human interventions you need and how long each of them is. Conversely, if we can make human interventions cheap and inexpensive, well, then we can spend more time with the human and rely on less universal autonomy. And this is an argument for adaptable autonomy. What does this look like in practice? Well, we need inexpensive human assistance, right? Right now, human assistance, you're probably thinking, all right, I'm going to go out, I'm going to touch the system, I'm going to do something. Well, that's expensive. You got to get out there. You got to do the thing. How do we make human intervention inexpensive? One thing is we make the human remote, right? That cuts out transit time. The human doesn't need to move from their chair. They're already there. We can also now shift labor geographically, right? So we can move our labor with where the prevailing winds and finances make sense. And we do this by treating the human as an oracle. We're going to give the human the same problem that the system has and see if they can solve it. And we receive the same response. So they just slot in as a replacement. Here's an example of what we do. This is a picture you might see from a depalletization application. This is a bunch of boxes on a pallet. Normally our system tries to figure out where are the boxes that we can pick up. So we might get something like this. This is an annotation where we've color-coded the boxes that we've seen. We can ask a human to perform this exact same task. And the system doesn't know if it was done autonomously or via a human. In fact, we can make this a little easier. We can ask the human for just one box. All we need to know is what's the next thing we're going to pick up. Humans can do this pretty quickly. Bear that in mind. So we put this all together into a system we call Yonder. It's remote human real-time interventions for autonomous vision exception handling. That's a mouthful, so we just call it Yonder. We have packages coming into the cell. We have an arm that's going to be trying to pick them up into singles. When everything is known, when the autonomous system can handle it, it all works autonomously. When something new happens, when that distribution shifts, when that Candy Crush box comes through, it calls out for help to a human. Humans are sitting at their desk. They perform the exact same task the autonomy would. They identify the box. It goes back. The system continues. This is our standard operating procedure. So if you think about exceptions, remember I said sometimes you walk out to the cell and you got to touch it, and I said we're going to make the human remote. Well, that doesn't work in all situations. So there's a few different types of exceptions you might have. There's mechanical exceptions. A suction cup jams, the arm faults, something falls or spills or breaks. And then there's these vision exceptions. Traditionally, you would walk out for all of these. You would go out to the cell and deal with the situation. What we've done is we've split this. The mechanical exceptions you still need to walk out to. I can't remotely fix a broken box. I can't remotely clean up a spill. But all the vision exceptions, I can now handle remotely with these humans wherever they happen to be in the world. Remote human intervention is the key to unlocking adaptability, right? Because when you have an expensive human intervention, you need to minimize it, and so you need to handle most things with the autonomy. But if human interventions are cheap and easy and fast, well, now you can tolerate more of them. Well, that means you can have a less universal model, which means you can now just collect data that you only need to deal with the thing at hand and not things you may not ever see, which lowers your annotation burden, which leads to less data training for training, which leads to quicker model updates, which leads to this nice cycle where the system can adapt. Here's that cycle I was talking about. So you can start with a non-universal model, a model that only handles, the things you know you're going to see. Maybe not the ducks crossing the road, maybe just the cars. You can collect your exception data with the human interventions, because they're cheap, they're inexpensive. You can then annotate just those, train them some more, have a new model, and repeat the cycle. This is the model adaptation cycle. I see some nods, so good. The other cycle, some of you may be familiar with, is the ML data cycle, which looks very similar. Right? Collect data, annotate it, train it, and deploy it. There was a study a couple of years back that said that 80% of the time is spent on these two steps, collecting and annotating your data. The actual model training and model deployment is very fast. How do you spend less time collecting and annotating data? Well, how do you collect data? One option is in situ. You go on site, you actually collect the real data from the system you care about. Well, that's great. It gets you the data that is the distribution you care about. But it's also very time consuming because you need to wait for the data to actually show up. So people do lab collection. I'm going to build a system and then feed it data that I think is representative of what I might see. Right? All of these setups are basically little labs. This is the data I expect to handle. And then, of course, some clever people came along and said, we can just do this all in simulation. Basically make video games that pretend to be the real world, and we can generate all the data we want from any distribution we can write down. Let's look at annotation. If you have real data, the gold standard is to have humans manually annotate it. Humans are very good at this. They're also slow. Simulation data has this nice benefit that when you make the simulated data, you can get your annotations for free, because the simulator tells you exactly where everything is. Well, that's great. Now I've got all sorts of data and all sorts of simulation data and annotation, including things like this. This is something that we had, it's a simulated data set of a tote full of objects on a conveyor belt. And as far as I can tell, it is set in a Las Vegas hotel with a Vegas-style carpet beneath it. Why is this a problem? We never see anything like this, right? This is not representative of our reality. So if you do simulation, there's a lot of work to make sure the simulation reflects your actual reality. It's called the sim-to-real gap. That's one problem. It's also, if I don't know my distribution in advance, how can I simulate it well? So I'm going to argue that you can do your annotation via this remote intervention process itself. So I showed you this image before. This is an actual image of boxes on a pallet. Traditionally, we also see things like this. This is a slightly harder problem. This is a bunch of bags that we need to pick one out of. What's the annotation for this look like? Well, if you ask a human, they might draw you something like this. This takes a couple of minutes, right, to annotate all these bags and figure out where they belong. However, we can ask a human to just find us one. And that's really fast. Find us one bag. The response we're asking for, note, is not the best response. We're not asking for find us the perfect bag. We're asking find us a bag. It's an adequate response. And the response itself is not complete. We're not asking for all the bags. We're asking for just one. Do it as quickly as you can. We call this the single annotation paradigm. Instead of annotating all your images and all your objects, just give us one. And this greatly reduces the burden. How do we use this? Well, if you're familiar with learning techniques, particularly deep learning nets, you tend to have a fully annotated data set to actually train. Well, we can mimic that. We can take our individual annotation, our single annotation, and cut and paste it on a known background. And we can generate, in a sense, simulate some sort of synthetic data set that is fully annotated, that does play nicely with our current learning techniques. What's that look like? Well, if you do this in the traditional sense and train, fully annotate all your data, average precision is just a measure of how good the model fits the data. You get really good results, 92%. That's a production model. We can ship that. If you use just the single annotation, you get absolutely zero. The system does not converge. You cannot train with this data. But if you do this augmentation that I just showed here, we can get back up to 75%. Now that's not wonderful results. I will say 75 is a lot better than zero, but it's not as good as 92. But what's key here is this required zero additional annotation, zero additional human effort beyond what we get during normal operations. So coming back to this cycle, right? We have a non-universal model. We're going to get our exception data from the system. We're going to minimally annotate it. Leads to quicker training, an adapted model, repeat. What we've done with the single annotation paradigm is taken this down to no annotation. There's no need for humans in this cycle anymore. This is a fully automated, hands-off model adaptation paradigm. This happens during normal operations, no labeling team, no outsourcing. It's all there. So coming back to this question we had originally, right? Universal or adaptable model. See where I've got on the bottom, I think it comes down to what is the control you have over the input to your system. I have that down here in the bottom, and I have just time on the vertical axis. There's this idea of how long will it take you to get to a universal model. Well, the less control you have, the more time it takes because you need to handle more things. If I know I'm going to handle just this single object, I can get to a universal model really quickly. And it used to be, above this line, that was your product, right? If I can make a universal model, I can deploy it, I can sell that. Below this line, couldn't do it. I don't have enough time to build a model that will actually work. And so there was a lot of work on pushing this line down. Simulated data, better learning techniques, faster computation. Push this line down so we can get more product. I think there's a different view. So again, above this line, universal, great. You can ship that, that's wonderful. But below, this is where you want an adaptable model. This is a model that changes with your distribution as it shifts. In my mind, it's a lot like one sizing versus right sizing. I see a bunch of boxes being made over there, apropos. A universal model is a giant box that you can put anything in. It can handle whatever comes along. Here, it's handling a box of, I believe that's some shampoo, or maybe nail polish. But the box is much too large. A right-sized box fits just the thing you care about. It does the job and nothing else. And if you have the ability to change your box, then I think you're golden. So the question I ask now isn't, what's your distribution? I ask, how much in control are you of your distribution? Can you change it? Do you know what you're going to get? And how much time do you have? Do you need something that works right now, or can you wait a month? Does your distribution shift quickly or slowly? It's the evolution of your distribution that really defines the system needs, not the distribution itself. You want to hear more about this? I'm happy to talk. We have a ProMat booth over there. Welcome to come, or shoot me a line, or visit our website.